Hello. This presentation is about our tangible programming system that young children can use to program robots with camera-enabled devices such as smartphones or tablets. There are many advantages of using robots to teach children. They can be used for mathematics, physics, and other STEM subjects. They increase children's problem-solving and creative thinking skills. They foster teamwork and collaboration. Children are more engaged and have a better attitude. Many of them develop further interest in computer science or other STEM jobs. And finally, robots can be used to teach programming, which is viewed by many as the new literacy. But there are also difficulties. Buying robots for entire classrooms is expensive. They also require a great deal of maintenance. In order to reduce the number of robots, teams must be formed, but teamwork is difficult when using a computer or a tablet to program the robot. And finally, the programming language and the style varies from robot to robot. Tangible programming languages, that is, those whose elements can be physically manipulated without using a computer, help with some of these issues. In informal settings, such as museums, people are more likely to interact with tangible than with graphical interfaces. These interfaces are better for teamwork since all children can play at the same time. When giving programming tasks, children finish faster with tangible interfaces. They also make less mistakes and are able to debug more of the mistakes that they make. Typically, children are more engaged with the tangible languages. They also create more complex programs and use a greater variety of commands. However, there are also some problems with tangible languages. They're not very common, first because there aren't many languages of this kind, and second, because amongst the ones that have been created, many are not commercially available. The ones that do exist and are of public access are designed for single use. Most are expensive because they rely on electronic components, and many of them are also more limited than the typical block-based languages. In order to deal with these difficulties, we propose the programming system Tactode. It has puzzle-like pieces and a mobile application. Once the pieces are arranged, the code is captured to the application using the camera. The application automatically recognizes the code and compiles it to the desired platform. That is, it creates a file with the code that the execution platform can understand. For example, these are the tactile pieces that can be used to make a square. Reading from the top to the bottom, when the flag is clicked, we repeat 4 times 2 instructions: go forward and turn left. The tactile pieces all have the same basic elements. A title that says what the piece does, an image which illustrates it, an Aruku tag that is used by the mobile application to identify the piece, and puzzle-like tabs that can be used to attach each piece to the others. The pieces are assembled from top to bottom with the arguments on the right, such as the 4 next to the repeat in the previous slide. There are also pieces with indentation. The if piece, for example, has the bottom tab slightly more to the right, so that when the code is assembled, it becomes clear which pieces will be executed only when the condition of the if is fulfilled. The Tactode mobile application is very simple. The main screen allows the users to set the program name, click the camera button to capture a photograph of the code. Then the application compiles the code, and if everything is alright, the user can export the code to the final platform or save it to the cloud. If the code has errors, they are reported so that the user can fix them. There's also a page where the previous programs are shown, and a settings page that allows the user to choose the platform between Cosmo, Ozobot, Robobo, Scratch, or Python, which are the platforms shown on the right. The user can also decide if the camera or a file, perhaps of a previous photograph of the code, should be used to obtain the tangible code. Our system is still in development, but it is already quite capable. So, we decided to use a focus group to do some preliminary experiments. We wanted to determine if children could use Tactode to build and execute simple programs. We also wanted to see their reactions and to get feedback for future developments. In our experiment, we decided to use the Ozobot Evo platform as a destination to solve a simple maze. The students were instructed to create a program in both languages, Tactode and Ozoblockly, that when executed would get the robot to solve the maze. Our instructions are used to control all the movements of the robot, particularly which way to choose when faced with an intersection. The maze is a series of connected straight lines with the exit marked in green. We created a guide for the teachers to follow. The teachers explained the strategy necessary to solve the maze, and the students had to program that strategy. The code the students were supposed to create is shown in this figure. The robot repeats a set of instructions until the line is green. First, it follows the line until the next intersection. Then, it chooses a direction with the priorities left, forward, right, and finally back. Basically, this code tells the robot to always choose left unless it is not available. A total of 22 students between the ages of 10 and 12 were organized into groups of 2 or 3 elements and asked to create the code in incremental steps. About half the groups used Tactode and the other half used Ozoblockly. Then the groups switched. It took about an hour to explain and distribute material, plus another hour for execution. Some groups asked for assistance and were given helpful tips. The light in the room caused some reflections, which increased the difficulty of taking a good photograph of the code. We observed that the groups using Tactode were more engaged, while the other groups were less focused and experimenting with different commands. We asked the students some questions after the experiment. The answers were given from 1 to 5, where 1 is nothing and 5 means completely. First, we asked if they understood the objective of the experiment. 5 students answered 4 and 14 answered 5, so they all understood what was asked. In the second question, they were asked to say if they found the language easy to use. Only 2 students answered 3, and the rest answered 4 or 5. So we can conclude that they understood it, most of them at least. We also asked if they thought the application is easy to use. Most answered 4 and the rest 5, so we can conclude they did find the application accessible. We also asked the students to choose a language, both for being easier and for being their preferred. Nearly 60% of the students chose Ozoblockly, both as being the easiest one to use and the one they preferred. We reached the following conclusions with our focus group. Tactode works and the children both enjoyed themselves and learned. Future developments should focus on improving the quality and speed of capturing the code through photograph, and also on reducing the steps needed to execute the code. But this depends on the implementation of each robot. For example, with Cosmo, we can send the code directly from our application to Cosmo's application. Some students, especially the older ones, prefer the graphic language. However, if we used smartphones instead of tablets, this interface would be nearly impossible to use. Regarding our initial objectives, we observed that our system is portable, that is, it can be used in any classroom or even outside. It works with a simple smartphone that the students can share. You can also use tablets or computers. There are already several platforms, one of them of general use code, Python, but more platforms can be added in the future. Using the robots to execute the code is better because it helps to make programming more concrete. Tactode is cheap because it doesn't have any electronic components. Also, it has both simple and complex programming constructs, as well as multiple programming paradigms. The Tactode tangible programming system is still in development, and it is our hope to improve it in the near future. Please do not hesitate to contact us through the webpage or email. Thank you very much for your interest and attention. Goodbye.